Hey, it's me again. I just wanted to show you a quick demo of what I was talking about before with the clocks. So I've hooked up my oscilloscope to the demonstration that I just gave you a little while ago of that microcontroller and the LED display. I've hooked up my oscilloscope to the significant data lines, and I've got it frozen here right now. So you can see the red guy, that is my clock, and the yellow guy is my data line, and the purple one's one I didn't talk about. It's not important. Well, it's important. It's not important for this discussion. So you can see, if you look at this line here, the dotted line, that as an alignment, you can see that the leading edge of this data is on that line. Um, the leading edge, the leading edge of this clock line would be reading a 1. Let's go to the next clock signal. That's the rising or the leading edge of that low to high transition. It's going to read a 1. Let's go to the next one. Low to high. It's going to read a 0. Next one, low to high, reads a 0, and so on. And let's just have a quick look at. There's another one. There's another one. There's some data that has a 1, 1, and 1, 3 ones in a row. Now I could have in the software just left the signal high this whole time, because it would still read a 1 on that leading clock's edge. 1. It would read a 1 there. It's unimportant for this to have gone down to 0. The only reason I would do that is because this consumes less energy for these lines to be down at the ground level. They're consuming no electricity or very little, whereas they're consuming a small amount when they're up. So it's just my habit to always pull the line down when I'm not using it. And in any case, you can see that the computer would have a hard time understanding all these zeros. Where do they start and where do they end? Well, that's what the clock defines. The leading edge of the clock says, here's a 0. Leading edge of the clock says, here's a 0. Here's a 0. Here's a 0. Here's a 0. Here's a 1. Here's a 1. Here's a 1. Here's a 0. Here's a 0, and so on. Now, the only thing that's left is to understand where a word starts, or where a byte starts, and where a byte ends. And that is the importance of this. It's probably not going to show. Yeah, you can just see the trailing edge of this line here. That's the select line. When that line is high, it's not talking to you. When that line goes low, you start listening. And once the clock starts, that's the start of the first byte. And so on. You just go on. Every 8 bits of the clock is another byte. That's all there is to it, believe it or not. And there are specialized chips and circuitry. That's what all of this stuff was all about. These flip-flops do exactly what that. You feed a clock into this series of flip-flops, and it outputs the data that's stored in the memory cells, because it reads on the leading edge. It'll read the state of that memory cell on that leading edge, and that's called a shift register. And that's what the Max 7219 LED display is every one of the 8x8 modules has its own shift register that's capable of being addressed. You can say, I want to talk to the top row. I want to talk to the second row. I want to talk to the third row. I want to talk to the fourth row, and shift out these 8 bits to that row. And that's how you turn those LEDs on and off, is by addressing each row, each display with a signal like this, that it can then, through timing, know exactly whether to turn that LED on or off. And it's not a decision process. It's just a matter of, when that bit is high, that thing's on because there's current going to it. And that's as simple as you can get in electronics. It is absolutely, in digital electronics, that's absolutely how things are done. That's the fundamental mechanism of a computer, is a flip-flop. And this SPI protocol is a good demonstration of how clock drives everything in the computer world. Anyway, so I just wanted to add that because I didn't think my previous explanation was all that good. Hopefully this one was a little clear. Thanks for watching. Cheers.